Okay, so did you find where we made the mistake?
Just before we start, can we turn off the app?
Sure, go ahead. Over there. Over here. Probably. Other one?
XJ 얘는 R2 and R2 이제
No, that's true. Everything is true. Just try to remember something from your calculus courses. I mean, you were probably getting mad at your assistants who were grading your exams, thinking that it was stupid to lose points from not writing some expression. Everything we did here is true, but we can only do these manipulations if R is non-zero. Now let's go back to this exercise over here. What we had done, I mean, you see the result of this integral. Okay, it turned out to be non-zero, but it also turned out to be independent of R. So kind of we can change our integration domain, but nevertheless, the value of the integral doesn't change. That basically tells us that our integrand is zero in all those ranges. So that was actually what we had calculated. But the sphere, a point is not a sphere. So as long as we are talking about a sphere, the integral is independent of the size of the sphere. This also confirms the fact that the Laplacian of 1 over R is zero if R is not zero. Because that is the domain we can take into our integration region or take out of our integration region, and the result doesn't change. But still, the point R is equal to 0 remains. So now we have to define some weird function. But before going to the three-dimensional example, let's look at the one-dimensional case. Let me define this function, the step function. So I have this function which is 1 if the argument is larger than 0, it is 0 if the argument is less than 0. Well, the value of x equal to, I mean, you will see this function quite often in physics, and its value at x is equal to 0. Well, you have to define it depending on where you're applying it. You can choose, sometimes you have to choose it to be 0, sometimes you will have to choose it as 1, sometimes you will have to choose it as 1 over 2. But at least for our example, it won't be really relevant. Now let me look at the theta by dx. If x is larger than 0, it is 0. If x is less than 0, it is still 0. Now let's look at its integral. From a to b. And let's just keep in mind that, let's just choose a and b such that a is less than 0 and b is larger than 0. Well, the fundamental theorem of calculus, on one hand, we know that at everywhere except then maybe 0, this function is 0. So naively, we would expect this integral to be 0, just like in our previous example. But if you use the fundamental theorem of calculus, which tells us that if you are integrating the derivative of a function, then the integral is nothing but the value of that function, the difference of the values of that function between the two endpoints. Now, a is less than 0, so we know that theta a is 0, but b is larger than 0, theta b is 1. So this is equal to 1. Again, a weird function. It is almost everywhere 0, but that function somehow it's integral is finite. Now that function we call the Dirac delta function. Dirac delta x is equal to 0 if x is not equal to 0. But of course, since that function is non-zero only at a single point, nevertheless its integral is finite, its value at that point has to be infinite. Because the integral is basically the width times the height. The width is 0. The height we don't know, but if we multiply it with 0, we want it to be finite, 1. So it has to be infinite. If x is equal to 0, such that the integral of Dirac delta x over x, let's say from 0 minus to 0 plus, from a number just to the left of 0 to the number just to the right of 0, this should be equal to 1. So this is how we define the Dirac delta function. This is the definition. Well, you can define the Dirac delta function as a kind of some limit. Let's say, for example, let's consider this function. Dirac delta tilde, let's call it. This is equal to 0 if x is less than minus a, 0 if x is larger than a, and 1 over 2a if x is between minus a and a. Basically just a step. So this is minus a, this is a, the height is 2a. This is the function. Now, of course, this depends on a.
1 over 2a.
Yeah, 1 over 2a, you're right. The area under this rectangle is always 1. So the integral of Dirac delta tilde of a of x dx, let's say from minus infinity to infinity, this is always 1, independent of the value of a. And Dirac delta of x, you can just write it as the limit as a goes to 0 of this Dirac delta tilde a of x. It satisfies all the conditions. Its integral is 1. It is 0 everywhere except, this Dirac delta tilde function is 0 if x is larger than a or smaller than minus a, but we are taking a to 0. So if x is not equal to 0, then this Dirac delta tilde function, this limit will be 0. If x is 0, then the value of that function is 1 over 2a, and when we take the limit a goes to 0, it becomes infinite. Just like the Dirac delta. Furthermore, its integral is the same. It's the Dirac delta function. Well, this is one, let's say, representation of the Dirac delta function you can use. Now let's look at one more representation. Let's look at this function. What is the integral of this function from minus infinity to infinity? Do you remember how to calculate this integral? Well, you see, if you want to calculate this integral, let's say I is equal to dx e to power minus x squared from minus infinity to infinity, just look at I squared, which is the integral over dx dy e to power minus x squared plus y squared. Go to cylindrical coordinates. And this integral, the integral for I squared is easy to evaluate. Then you will see that I is equal to square root of pi. Well, we have this sigma. You can get rid of that sigma by just a change of variables. And this integral just becomes, let's say this is sigma squared square root of pi times sigma. So basically, if you have minus infinity to infinity, e to power minus x squared divided by sigma squared divided by square root of pi times sigma, this is equal to 1, independent of sigma. Now furthermore, if you just would plot this function, let's say delta sigma of x that function looks like this. So basically sigma is somewhere over here. If you, and the area below this curve is always 1, whatever the value of sigma is. So if you make sigma smaller, and the maximum value over here is 1 over square root of pi times sigma. Now if you make sigma smaller, it will become narrower, but higher. So this is a larger value of sigma. And again, if you take the limit sigma goes to 0, you see if the x is larger, much larger than sigma or much smaller than sigma, the function is basically 0. Now if you take the sigma to 0, if you let sigma equal to 0, this exponential, if x is non-zero, this exponential just becomes e to power minus infinity times some number. Now that is just 0. If x is equal to 0, then this function is just 1 over sigma. If you set sigma to 0, then it becomes infinite, just like the Dirac delta. So if you take the limit as sigma goes to 0 of delta sigma of x, it is 0 everywhere except an x equal to 0. It is infinite at x equal to 0. And well, since whatever the value of sigma is, its integral is always 1. So in this limit, if you take that limit and take the integral, again, it's just 1. The integral is 1. That is the definition of a Dirac delta. Now, there are many different representations of Dirac delta function. These are just the simplest two of them. It's nice to integrate the Dirac delta function. Let's say from a to b, Dirac delta x minus x0 times f of x dx. Let's look at this one. Well, there are various possible cases. x0 can be in this interval between a and b, or it can be out of this interval, a and b. Now, if x0 is not in this interval between a and b, then the argument of the Dirac delta is never 0. Since it is never 0, it is always, the value of this Dirac delta is always 0. Well, you are integrating 0 over an interval, that is 0. So this is equal to 0 if x0 is not in this interval.
Can you repeat this?
Hmm?
Can you repeat this?
So let's first assume that x0 is not in that interval. x0 is either less than a or larger than b. Okay. Now, what do we know about the Dirac delta? Its value is always 0 if its argument is non-zero. So if x0 is always less than a, if x0 is less than a, you see in that integral, I mean, whenever you see an integral, it's just a sum. Just give different values to x and sum their values. So x always takes values from a to b. But x0 is less than a, so in that range, x is always larger than x0. But that means x minus x0 is always positive. If x minus x0 is always positive, then Dirac delta, the argument of the Dirac delta is always non-zero. But that means the value of the Dirac delta is always 0 in that interval. So basically, this integral just is 0. Same argument holds if x0 is larger than b. If x0 is larger than b, then in the integral, x is always less than b. Since x is always less than b, x0 is always larger than b, x minus x0 is always less than 0. Since it is always less than 0, it is always 0 in that integral. Since it is always 0, it is just 0. The integral is always 0. Now let's look at the other case. If x0, no, sorry, I wrote something wrong here. If not. If x is not in that interval. Now let's look at the case if x0 is between a and b. Well, we can divide, let me first divide this integral from a to x0, let's say minus, just to the left of x0. Then from the left of x0 to the right of x0. Then from the right of x0 up to the point B. So what I'm doing is I have this, let's say, real line. A is somewhere over here, B is somewhere over here. I'm saying that let's assume x0 is somewhere in between A and B. Because we had already seen that if x0 is not between A and B, the integral is 0. So I'm dividing this interval into 3 regions. I start from this point, then go up to this point over here, and then from this point to that point, and from that point up to the point B. So those are my 3 different regions. I'm dividing my integral into these 3 regions. Well, in the first region, x0 is the point that makes the argument of my Dirac delta equal to 0. That's what's special about x0. In this first region, let's say this is the second region, this is the third region. In the first region, Dirac delta is always 0. So the integral is 0. In the third region, again, the Dirac delta is always 0. So the integral is 0. So I'm only left with the second region. So from A to B, Dirac delta of x minus x0, f of x dx. This is equal to, from the left of x0 to the right of x0, Dirac delta of x minus x0, f of x, d of x. Because everywhere else, the integrand is 0. Only in this place, the integrand is non-zero. Furthermore, it is infinite. But you see, we are talking about a very small range of x. And eventually, I mean, we can even take that limit, the size of that very small interval to 0. Because Dirac delta is non-zero only at the point. But if f is a continuous function, and physics, all the functions we will be dealing with will be continuous functions. So in that very small interval, the value of f does not change. So it is, and its value is equal to f of x0. And this integral, we know the properties of the Dirac delta. We know that its integral is 1 over a region that makes its argument 0. So basically, what this Dirac delta function does is, if there's a Dirac delta function inside your integrand, you can evaluate that integral even if you don't know what the function f is. It just tells you that wherever you see x, just put x0. Conceptually, it's kind of difficult to understand what this function is. Mathematicians don't even call it a function, they call it a distribution. But for us, we will just call them functions. And the integral is kind of trivial to evaluate. Of course, we will also have cases where we will have Dirac delta of some function of x. Now, again, the only contribution will be from points which make the argument of the Dirac delta 0. So let's say, let xi be such that g of xi is equal to 0. You can have many functions that will make that function g equal to 0. In that case, Dirac delta of g of x will be equal to, well, we will only receive contributions from the point x is equal to xi. Well, this will be trivial. It will be quite nice. There is a slight complication, though, divided by g prime at xi. Well, basically, you are making a change of variables in the integration. Instead of integrating over, I mean, what you can actually show is from xi minus to xi plus Dirac delta of g of x f of x dx. Well, this is equal to f of xi from xi minus to xi plus Dirac delta of g of x dx. Now let's make a change of variables. Let me call u is equal to g of x. So du will be equal to g prime of x dx. So this is equal to f of xi from xi minus to xi plus, well, let me call it, I'm integrating over u, ui minus ui plus Dirac delta of u. No, sorry, not ui minus ui plus. It's from 0 minus to 0 plus. Remember, x is equal to xi just makes u is equal to 0. So it's 0 minus to 0 plus Dirac delta of u dx du divided by g prime of x, but of course as a function of u. So that integral, remember, the integral of Dirac delta just tells us that instead of u, we should put 0. F of xi, 1 over, no, there is no absolute value at this step. 1 over g prime of xi. There is an absolute value in this step, though. Or maybe we should better put it in this step. Why there is an absolute value?
Because it's chosen from before 0 to after 0 without knowing what g is.
Kind of, yeah. Essentially, yes. In more detail, let's say the problem is we said that, okay, g of xi minus. We don't know whether, we know that g of xi is 0, but if we are slightly to the left of xi, we don't know whether it is slightly below 0 or slightly above 0. It depends on the derivative. If the derivative is positive, in that case, this is equal to 0 minus if g prime at xi is larger than 0, and it is equal to 0 plus if g prime of xi is less than 0. So since I fixed the order of integration at this step from 0 minus to 0 plus, I have to add a plus sign or a minus sign. Well, you see, when we are making a change of variable, the lower limit should correspond to xi minus, and the upper limit should correspond to xi plus. But when I'm saying that it is from 0 minus to 0 plus, it is true if the derivative of g is positive at xi, but if the derivative of g is negative at xi, that means I have already made a change of variable, change of the order of integration, change of the limits of the integration. So there is an additional minus sign. So if g prime is negative, I put a minus sign. So minus g prime is positive. If g prime is positive, I leave it as it is. So that is the definition of the absolute value. That is why I have an absolute value over here. Of course, this is the contribution. This result is the contribution from only one of the zeros of the xi to take into account all the possible contributions. So basically, this is the identity we have. Some of those Dirac deltas might contribute, might not contribute, depending on the limits a and b. Only the Dirac deltas that are 0 within this interval will contribute to the integral.
What if g prime xi is equal to 0?
Okay, there are some, let's say, if g prime is 0, then the integral is divergent. It is not finite.
Because we have constant 0, or the argument of delta.
Now, let's say if g prime is 0, that basically tells you, in a sense, kind of, it's in a, you have the Dirac delta is 0 in a finite interval. Almost. If it is, but it's an infinite function. If it is 0, not, it is infinity in a finite interval. Infinite times a finite number is infinite. So it diverges. So if g prime is 0, the integral is divergent. Not all integrals are finite. Well, in physics, we just hope that we never have such cases. Of course, there's the other extreme case. I mean, here in the definition of the Dirac deltas, if you pay attention to, I didn't add any equality signs. I considered the case if x0 is less than a, x0 is between a and b, and x0 is larger than b. What happens if x0 is equal to a? Well, those are pathological examples. I mean, sometimes you do see them, but you have to avoid them as much as possible. Well, I will just discuss an example where you cannot really you can avoid them. But depending on the, let's say, the boundary conditions or the conditions of your problem, you have to define whether to take all the value of the Dirac delta. If the Dirac delta is right at the boundary, you can just think that it is outside your boundary and you are taking the limit. You can think that it is inside your boundary and taking the limit that it moves to the boundary. Or you can say that half of it is on one side, half of it is on the other side. But it will depend on your problem. But these things, especially if you are using computers, you have to pay attention to what does the computer assume. Is it the correct assumption? Let's also consider the three-dimensional Dirac delta now. Well, the definition is basically the same. So this is equal to 0 if r is not equal to 0. So it is 0 almost everywhere except on a single point. And if you integrate this three-dimensional Dirac delta over a volume, let's also put some function f multiplying it. This is equal to f f of R0 if R0 is in your volume, and this is 0 if R0 is not in your volume. In fact, this is the definition in arbitrary number of dimensions, but for us the relevant one will be the three-dimensional case. And, well, in various coordinates, you can, for example, write this as Dirac delta x, Dirac delta y, Dirac delta, x minus x0, Dirac delta y minus y0, Dirac delta z minus z0. Well, it satisfies the criteria. It is 0 if x is not equal to x0, or y is not equal to 0, or z is not equal to z0. It is non-zero only if x is equal to x0, y, only if R and R0 have the same x, y, z components. So that is if R and R0 are equal. If they are not equal, it's 0. If you consider the integral, the volume integral will be always dx, dy, dz. All of them, you can just treat them as one-dimensional integrals. X, y, z. You can just start by taking the z integral. Dirac delta z minus z0 just tells you that just wherever you see z, put z0. And similarly, you can take the y or the z integral, so this will just become f of x0, y0, and z0. Well, let's also consider the spherical case. So are you familiar with the spherical coordinates? Yes, no?
Not really.
Let's first define them. I mean, in most of your lectures, we said, oh, you already know the spherical coordinates, so let's use them, right? So let's just define them first. So there is this angle over there. This is what we call the theta angle. Theta takes values between 0 and pi. Inclusive, yes. Then we have the perpendicular projection on the xy plane. This angle is what we call the phi angle. Phi takes values between 0 and 2 pi. It can't have value 0, but usually 2 pi is left out. And then this distance is r. R can take values between 0. R is larger than 0. So these are the three coordinates. R, theta, and phi. Now, the nice thing about these spherical coordinates is if you want to write the position of a particle, it's kind of trivial. It's in the r hat direction. That is the direction toward our particle. But of course, if the position of your particle changes, this r hat changes. You see, the nice thing about the x, y, and z coordinates, x hat, y hat, and z hat, is no matter which position you are talking about, x hat is the same vector, y hat is the same vector, z hat is the same vector. But if you are using spherical coordinates, let's say this is our origin, if you are looking at a particle over here, r hat vector points in that direction. If you are looking at a point over here, r hat vector points in that direction. So, for example, that is something that complicates the expressions for the divergence and curl in various or Laplacian in various coordinates, because you also have to take the derivatives of the unit vectors. They change from point to point, so their derivatives are non-zero. Now we can talk about the derivatives of these vectors. The derivative of r hat with respect to r, this is 0. Derivative of r hat with respect to theta, this is what we define as a theta hat vector. And the derivative of r hat with respect to phi, this is also almost phi, a unit vector. So this is a third dimension we define. It's almost a unit vector, but the normalization is not unit, so it is sine theta phi hat. Now the nice thing about this is that, I mean, they are orthogonal to each other. Well, that we already know, because if you consider r hat squared, this is equal to 1. And if you take, now since r hat vector changes from point to point, it depends on theta and phi. It's a function of theta and phi. So we can consider the theta derivative of this r hat squared vector. This will be equal to 2 r hat scalar product derivative of r hat with respect to theta. This should be 0. So r hat, derivative of r hat vector with respect to theta is orthogonal to r hat. Similarly, if you take the derivative with respect to phi, this is twice r hat by that phi. Again, the derivative with respect to phi is orthogonal to r hat. So r hat is orthogonal to theta hat, r hat is orthogonal to phi hat. Well, this is not a proof that theta hat and phi hat, they are orthogonal to each other, but let's say it's left as an exercise. Theta hat and phi hat, they are orthogonal to each other. And it's just like the x, y, z coordinates, x hat, y hat, and z hat, they are orthogonal to each other. But this time now we have 3 vectors at every point. They are pointing in different directions, but nevertheless there are 3 orthonormal vectors: r hat, theta hat, and phi hat. And there is nothing that forces us to use the x, y, z coordinates to describe the position of objects or events. We can as well just use our theta and phi coordinates to determine the position of events. But of course, we have to somehow modify the expressions. For example, the volume element in Cartesian coordinates is easy. In spherical coordinates, well, it will be dr, d theta, d phi. It should be proportional to this one with some proportionality constant. Well, there are one way you can just make a change of variables. You can consider this as a change of variable. And if you make that change of variable, you have the Jacobian over here. Are you familiar with this Jacobian change of variables in multidimensional integrals? Well, let's take the absolute value. Or you can go for a more, let's say, physically intuitive calculation of this factor. Let's try to calculate this volume element. You see, when we are talking about dV, what we are actually doing is you start from a point, change the x coordinate by the x, change the y coordinate by the y, change the z coordinate by the dz. It gives you a small cube. And the volume of that cube is what we call dV. You just change your coordinates by very small amounts and calculate the volume of the cube that you obtain. We can do the same thing in spherical coordinates. Let's start from this point. Now, starting from that point, of course, we have all these. This is theta. This is phi. Now we can change the r coordinates slightly. So from that point, we come over here. That is dr. Now then we can change the theta coordinates slightly. We will have an arc. Well, it will change in the opposite direction. So this length is dr, this length is not d theta, it's r d theta. Now, of course, we also make a similar change over here. This is dr. So we now have the area element. The area element that is in the phi hat direction. The A is equal to r d theta times dr. This is the area, and it is in the, no, this is not theta, this is phi. It is in the phi hat direction, for example. So this way you can write down the area elements. Now, of course, we have this area element, which we obtain by changing theta and r. So it's basically in this plane. You see, we are fixing phi. If you fix phi, you obtain a vertical plane. This is fixed phi. In this plane, let me rotate it slightly. I changed r, so it gives me this length. Then I change phi, it gave me this arc and this arc. So here we have a very small area. Now we are changing phi. By changing phi, we are basically rotating this plane as a whole, right? So this point over here, let's say this is my z-axis, this point over here is rotating around the z-axis by phi. What is the length of that segment? R, because this length is r sine theta, it is rotating around the z-axis. R sine theta is rotating by d phi. So we have this rotation over here. This length is r sine theta d phi. Now we obtained r cube dv. One side of that cube is dr, the other side is r d theta, and the third side is r sine theta d phi. So the volume element in 3 dimensions is r squared sine theta d theta d phi, or r squared d cosine theta d phi, whichever one you prefer. Now, by the way, this is usually called the omega, the solid angle. Are you familiar with the solid angle? Well, how do you define an angle? Ordinary angle, not the solid one. In radians, what is the definition of radians?
The amount of matter that corresponds to one.
The amount of what?
The angle that corresponds.
What do you mean by an angle? We are defining the angle.
Length of a curve.
You take a circle. You take a circle, arbitrary units, let's say, arbitrary size. There is this length of this arc, let's call it L. The radius is R. L over R is what we call this angle theta. No, theta, not the spherical coordinate theta, but angle at theta, or let's call it a different name. So basically, in 2 dimensions, it also tells you a direction. So in this case, it is that direction over there, somewhere over there, a range of directions. Now, the solid angle is similar to that one. What would be the generalization of a circle to 3 dimensions? A sphere. You take a sphere. Well, on a sphere, you don't talk about the length, but you talk about the areas. So you take an area over here. An arbitrary area, it doesn't have to be rectangular. And then you just connect it to your center. That kind of gives you a cone. And this angle here is what's called omega, the solid angle. And the definition is the area divided by r squared. So let's say, from this definition, what is the total solid angle? Well, the total area is 4 pi r squared divided by r squared, so it is 4 pi. And d omega is actually this one, d cosine theta d phi. If you just consider a very small area over here, it will correspond to some angles between theta and theta plus d theta, and between phi and phi plus d phi, a very small area. And then if you just calculate for that, for this area,
Should we have dr?
where?
Dr.
In the omega? No,
dv.
in dv. dv we have r squared. Dr, yes, you're right. So this is a solid angle. And actually, if you put in the theta and phi limits, cosine theta changes from -1 to 1, and phi changes from 0 to 2 pi. The integral is actually 4 pi, as it should be. And let's write now before you go, let's write down the Dirac delta in spherical coordinates. Well, if two vectors are equal, they should have the same components, whatever components you use. In this case, we are using the spherical coordinates. So their spherical coordinates should be equal. So r should be equal to r0. Phi should be equal to phi 0. And theta should be equal to theta 0. Almost. Now, why do we have that r squared sine theta? Well, here we have r squared sine theta. So one-dimensional Dirac deltas, they already give you, integral gives you 1. There shouldn't be any function multiplying them if you write the three-dimensional integral in terms of r theta and phi. So this factor over here should cancel this r squared sine theta in our expression for dv. And the result is just dr, d theta, d phi, r squared sine theta, Dirac delta cube, r minus r0, f of r. This is just f of r0, thanks to these factors over here. So those factors have to be there. Now, there's one problem. Well, let me just mention one possible issue. What if R0 is at the origin? R0 can be at the origin. There's no problem with that. And the integral should still be 1. But if you look at the R integration, this R integration goes from 0 to infinity. The theta integration goes from 0 to pi. Phi goes from 0 to 2 pi. Well, Dirac delta R minus R0 is just Dirac delta R. Dirac delta is right at the boundary. But we already know that the integral should be 1. So although the Dirac delta is right at the boundary if R0 is at the origin, we should still consider that Dirac delta inside our boundary, inside our integration region.
What if it was on the outside boundary?
Now, you see, in this example, we know that if we are integrating over a volume which contains the origin, the Dirac delta gives its full contribution. We already know that. If you want to use the spherical coordinates to describe that Dirac delta, then there's an ambiguity over there. Dirac delta is right at the boundary, and you have to somehow resolve that ambiguity so that the result is correct. We already know the result. Okay? So we already know that although the Dirac delta is at the boundary, we should consider it as inside our boundary in that case. Now, since R integration starts from 0, if it's out of the boundary, it just means R is less than 0. That doesn't have any meaning. R, by definition, is positive.
What if theta is from 0 to pi over 2?
You see, if here I'm just considering the case we are integrating over all space. You don't have to. You can just take a, let's say origin is over here, your R0 is somewhere over here, you are integrating over this volume over here, then the integral is 0.
In this case, we are integrating only half this cube.
If theta goes from 0 to pi, this is the plane. Okay, where is your R0? Where is the R0? Somewhere over here.
Somewhere at the surface of the thing.
Well, somewhere at the surface, I mean, again, you have to look at what is the, I mean, those surfaces do not really exist in real life. I mean, something is either on one side or on the other side. You have to look at your physical case. I mean, you obtain that very thin surfaces only by assuming that the thickness is negligible. Then you have to analyze your assumption and see whether you have to take all the contribution, half of it, none of it, in that limit. You have to consider the limit that you take the thickness to 0. And then determine whether you should take all of it or half of it. Any last minute questions? Okay, so see you on Monday. Okay, next week I will still keep on lecturing. So meanwhile, make sure that you find the book. A Google search will help you. And then after next week, it will be your turn.